Hello students. Yesterday we studied Nyquist stability criteria. Criterion. Okay. And which can be summarized by n equal to z minus p, or you can write as z equal to n plus p. Yeah. And what it tells you, where z is number of zeros of 1 plus gs times hs, okay, in the right S plane. Then n is a number of encirclement meant of minus 1 plus 0i, right, in clockwise direction, right? And then p is equal to number of poles of 1 plus gs hs in the right S plane. Yeah, and this is what all about, and this follows from the mapping theorem, right? So based on this, you can also find out the whether a system is stable or not. How? For stability, what do you need? For stability, there should be no poles and zeros in the right S plane. As simple as that. We know that, right? If we have anything in the right S plane, then this will not converge, right? So if you give for example, some disturbance, and in that case it is not going to come back to zero. Yeah, so because of that, it is not stable. That really means, okay. So on that we have seen already, if S plane, and if the roots or the poles or zeros are on this, then it is going to oscillate. This will be like oscillatory, right? For example, the spring mass system will have poles on this, for example, right? Okay. So all those things we have seen already. So for stability, we don't want any poles and zeros on the right S plane. Here we don't want. Everything we want this side, and for stability, that we know already. This Nyquist stability criterion gives you a tool that based on what the Nyquist plot tells you, based on that you can find out how many poles or zeros will be on the right S plane. Yeah, so maybe the number of poles, but remember that n equal to z minus p, difference it will give you. It is not going to tell it is not going to tell you what exactly n, what exactly p, unless you know for sure one of them. So if you know number of poles on the right S plane, then you can know everything. Then if you know the n, then you can see n here, right? So then you can say z equal to n plus p. If p is known and n you can see from the diagram, and you add them, you can find out how many zeros will be on the right side S-plane. Yeah. So it's important that you have to know one of them. Then only you will be able to predict for sure how many are there. Yeah. Sometimes GS and HS, GS times HS may have some 1 over S, something like this, and even something more here. Let us say S, and then here you have more thing. So more thing is maybe S plus A or something like this one. But look at this. What happens? This one is, you know that your S, before the mapping, what you do? You have this. Yeah, and this R is equal to infinity. And it passes through origin as well. But if you put S equal to 0 here, it is going to be infinite. And remember that what is the criteria? The first of all, we call it that GSHS has to be finite. Right? Even at infinity, it has to be finite. And we have seen why it should be finite also. So or 0 it becomes. But here, if you see S equal to 0, you put, this becomes a very big number. This approaches infinity. So in that case, remember, we don't have to pass through that origin. In that case, this is a special case. You can have a small circle here, like this one. Yeah. Let us say epsilon, let's call it. And you don't have to go through the origin, rather you can go like this. So you can bypass the origin in that case. Yeah. So you can go like this. Yeah. Where this is very, very small radius here. Yeah. R equal to epsilon. Epsilon is very, very small. Very, very small. Yeah, or say 10 to 0. Okay, so you can, in that case, you can take, you can assume one epsilon value, and put it there, and you can accordingly you can plot how it is. Yeah. So basically this will take care this kind of open loop transfer function. So remember that. What we see so far, that we have GSHS, and we have used for both. We have Bode plots. Also we can have for GSHS, and GSHS, GS times HS, also we can have for Nyquist. Okay, Nyquist plots. Now this is for open loop, and for the closed loop transfer function, right? Transfer function, this becomes TS equal to some value here. So there will be either G, basically not some value, but actually it should be GS, and then it will be 1 plus GS times HS. So this is a closed loop transfer function, right? What we see here, this one. So all the Bode plot or Nyquist diagram may be for the open loop transfer function, and from there we have to somehow we should be able to guess the few things about the closed loop for the closed loop system. That's what we have been doing. Yeah. Okay. Now here, remember that if transfer function is given like this one, this is going to be unstable. Okay, TS. What we are talking about? We are talking about the frequency response, right? So if you are talking about frequency response, if T, you put Tj omega, and we have G, J means I only, so Gi omega divided by 1 plus Gi omega and Hi omega, right? Okay, so what we get here, T is going to be infinite, right? So what we see basically simply that the magnitude, this infinite, this one, Ti omega, or magnitude you are putting that, right, is tends to infinity if there are two things. Simply we have 1 plus Gi omega Hi omega equal to 0 simply, right? And that really means that Gi omega times Hi omega equal to minus 1. Minus 1 means one value minus 80 degree, right? Magnitude is 1 and phase, this is phase, right? And this is gain. So gain equal to 1 unit and phase equal to minus 180 degree, or minus or plus minus, it will be the same 180 degree. So basically we have to avoid that situation. We don't want to have gain and phase both are 1 and 180 degree respectively, because the moment you have both together, it is going to cause it, make it unstable. Yeah? And how much we are going to, with respect to this, we are going to learn two jargons here. One is called gain margin, and second is called phase margin. Both of them are basically how far you are from the gain equal to 1 and phase equal to 180 degree. That's what it tells you. Yeah. Meaning that if this one, simply the gain margin is when phase equal to 180 degree, how far gain is from 1, and this tells you when gain is equal to 1, how far is the phase, from 180 degree. This is what it is. So that you know that you are safe. So that you know that you are stable and you are safe basically. In all of the examples, earlier we have seen that this angle is basically, we got negative only. So we got minus 45 degree, minus 90 degree, minus 80 degree, and so on, right? So basically, this is, in actual sense, there is no difference between 180 degree and minus 180 degree. However, when we are talking about the difference, and and all the angles, let us say, are here from 0 to minus 90 to minus 180. So when you say difference, automatically we have to take minus 180 only. So that will be the better way of we get the value which will be less than 180, right? So this phase angles, the phase gain has to be less than, if you are saying it, the value itself should be less than 180, and that is possible only when we consider this as instead of calling 180, we may call minus 180 as well, so that we have the positive. We don't have like whatever value we have, if subtract, let us say this value from here to here is, what is the phi between negative number, right? Okay, and this phi, yeah, and minus 180 will give you 180 plus phi. where phi is the this phase, right? So anyway, so here better we can put it minus 180 degree. Okay, so that way it will be easier when we derive it. So far what we have, gain margin when phase equal to minus 180 degree, how far gain is from 1, and phase angle when gain equal to 1, how far is the phase from 180 degree. Now this one we can write as equation as well, right? So we can say phase margin, let us say phase margin right here. So phase margin we can write margin, let us say gamma is equal to, so how far is the phase from this, so when gain equal to 1, how far is the phase? So phase when gain, so let's write it phi is the gain, phi is the phase when gain equal to 1. Okay, so basically phi equal to phase when gain or this GS times HS rather G I omega times H I omega is equal to 1. Yeah. So phi equal to phase when gain, this is gain, right? When gain equal to 1. So this becomes phase margin equal to gamma equal to phi. Phi is the phase when gain equal to 1 minus 180 degree. Okay, so phase from when, how far is the phase from minus 180 degree? So phi minus 180 degree. So that becomes 180 degree plus phi. Since phi is negative, right? Phi will be negative, and hence you will get a positive number, phase margin. If you are getting more negative, right? So it could be, instead of here, it could be here, right? So in that case, you will get negative phase margin. Yeah, you will get the negative phase margin in that case. So positive is this side. Yes, and we have seen for first order system we had 0 to minus 90 degree. For second order system we had 0 to minus 90 degree to minus 80 degree. Yes, so hence like this. So this phase margin you have like this. Now gain margin is calculated in ratio. Okay, so this gain margin, the gain margin, so let's call it Kg, gain margin, is given by 1 over Gs and Hs. So, okay, so G I omega times H I omega. Okay, where Kg equal to 1 over the gain, where at phase equal to, when the phase is, yeah, so this at omega, at some omega, at omega, that makes angle G I omega times H I omega is equal to minus 180 degree. Yeah? So basically what you are finding out? You are finding out what is the gain when the phase is, what is the gain 1 over the gain when the phase is minus 80 degree, right? So Kg is given by 1 over like this one. Yeah. So typically you also, like for example Bode plot, you have in decibel, right? So in terms of decibel also you can write it, right? So in terms of decibel you can have 20 log Kg equal to, you will have simply 20 log 1 yeah, a minus 20 log, and then let us say this is g I omega. So omega we can write 180 degree, so let's call it just p, something like omega p, right? So g I omega and h I omega p, yeah. And now you see, if you take the log, then it becomes a difference basically, right? So this actually, it tells you how far it is from the gain equal to 1. That's what that becomes now, yeah. Okay. So remember, when gain margin is positive, phase margin is also positive, yeah. So the sign will automatically taken care of by this, yeah. So here you can also see here that when you have phase margin, we have phi minus angle with respect to that we are measuring, right? In this case we have 1 that comes first, so it's not log of this minus log of 1, that we are not doing. We are putting this first, right? Because yeah, so that both of them are positive. If one is positive, the other is also positive. But if one is negative, the other is also negative, yeah. Okay, so this what that is, this becomes 0, so 0 or simply becomes minus, will be minus 20 log and gi omega p h I omega p, where omega p that is where you can write also such that angle g I p h I omega p is equal to minus 80 degree, right? Okay, so this is what the phase margin and gain margins are, okay, and these are also maybe the design criteria, okay. So that gives you basically idea how far it is from the instability, yeah. So that gives you the so basically accordingly you can design the system. So for example, if you have remember if you have transfer function Ts equal to s square plus say omega n square, something like just like that, okay. And you know that zeta equal to 0 in this case, and if you take the inverse Laplace transform, you will get the sinusoidal. This is representative of a spring and mass system, right? Okay, and in this case what do we see? This becomes at omega equal to omega n. What do we get? We get this value automatically Ti omega, okay, and if we take the okay, Ti omega will be 1 over omega square, omega n square minus omega n square, right? Omega equal to omega n, then Ti omega becomes omega n square minus omega n square. So this tells you the resonance basically, yeah, resonance, and this is indicative of it's not a stable basically, yeah. So this is how it reaches, just to understand the significance of that. Okay, so it also tells you the similar kind of situation is also there. Instead of having this Ts equal to 1 over s square omega n square, your closed loop system will have Ts equal to 1 over 1 plus g I omega times h I omega, right, or gs times hs. So if we have this one such that we get both of them, means if we have like this omega h I omega, if the gain is 1 and angle, the phase is also h I omega equal to minus 180 degree, that means it is also going to be the same kind of situation. You will have the 0 value here, like the you have the same value, same kind of thing will be here. Okay, so the physical interpretation is when you have this exactly equal to minus 1, then that really means that the roots are, yeah, the roots of this, all the poles of this may be on the imaginary axis, on imaginary axis. This is what tells you. Here also you can see, right, s square plus I omega, and hence you get s equal to plus minus I omega n, right? It tells you that, what does it tell you? It tells you that the poles or the roots of the characteristic equation is on the imaginary line, yeah, on the imaginary axis. Similarly, in this case also, if g I omega and h I omega turns out to be minus 1 at some omega n, that then you know that the roots of 1 plus g I omega times h I omega will be, or 1 plus roots of 1 plus g s times h s will be, somewhere will be s equal to plus minus I omega n. Yeah, so that's why it is making it all equal to 0. Yeah, so this is indicative of this basically. Yeah. So just to relate it with some physical example. Yeah, so this one is like a spring mass system, and here also you see the same kind of situation. Let's see with respect to Bode diagrams, what does this margin, the phase margins and the gain margin means. Okay, so let us say this is how it is. This is 1, okay, or what do we have? We have 20 log of g I omega. So this is I omega multiplied by h I omega, right? So yeah, so this is the gain, the magnitude basically we are talking about. Yeah, and this is how, this is a 0. So let us say this is coming like this. So we have, yeah, and then we have like this one. Yeah, so this one is, this is the point where the value is, this is 0 point, or the gain is 1, right? This is 0 point, and then we may have say minus 10, minus 20, and so on. It will go like this. Yeah, okay. Okay, now we have like this one. Okay, so this one where gain is equal to 1, yeah, so we have like this one, and then there will be somewhere where phase is going to be minus 80 degree, right? So let us see here this is a minus 80 degree, so this is minus 80 degree. Yeah, and this is the where it is crossing. Our angle could be something like this. Let us say, just a minute. So this is what the phase is, right? So our phase is angle of z I omega multiplied by h I omega, right? And let us say this is minus 0, yeah, and then this becomes minus 90, minus 180, and goes on, right? So minus 270 and so on, right? Okay, so minus, what you see here is minus 180, and you know, like you are measuring from minus 80 upward, right? So here this one, what is known as phase, the gamma or the phase margin, right? This is 0, and from here you are, this is the point where, which correspond to this, yeah, which correspond to 0. 0 means basically, 0 means here g I omega h I omega magnitude equal to 1. That's what it means, yeah? Okay, so this is a phase here. You can write here, this is a gain, this is phase. Okay, now this is you are measuring in terms of from here upward, see, positive, so you make like this one. This is a positive gain margin. Here you are measuring from here to here, and this is positive gain margin. Okay, positive gain margin. Okay, so at 180 degree, this is the point which is correspond to 100 minus 180 degree phase. So here at this point, this corresponds to the minus 180 degree phase. Okay, and you are finding out what is the gain here. So what you are doing, 0 minus the value of this is the gain, yeah? So whatever value you have here, but must be negative only, so you have 0 minus what is the value of this one, so that makes it positive, yeah? So gain margin, this is positive gain margin, this is the positive phase margin, yeah? So this is what in terms of the Bode diagram. Similarly, we can see in a Nyquist diagram how it looks like. Okay, so in Nyquist plot of the same thing. So in Nyquist plot you have like this, and then what do you have? So what do you want? This is minus 1, yeah? So this actually what we want is we can have a circle. Why? Circle tells you the gain basically, right? So we know that the radius in the Nyquist diagram, radius denotes the gain or the magnitude of g, right? So the magnitude of g I omega times h I omega is what the radius is. Okay, so this this point is, that refers to minus 80 degree, right? So this point has, this is what our reference, this point is the one which has one gain and angle is minus 80 degree. That's what it is, and from here we are going to measure, yeah? Okay, now let us say this is where the phi is, from here to your phi. Okay, so what is the meaning of phi? Okay, so phi is, let us say the Nyquist plot is something like this. Yeah, Nyquist plot goes from here, okay, and then goes here, and it will go like this one. Okay, so that means the phase, this point on the Nyquist plot corresponds to when the gain is 1, right? So this point is nothing but 1 gain and phase is this, right? Gain is 1, phase is 5. This point is gain, there will be some gain there, right? Okay, so this let us call it, the gain is some value g I omega, we call it p, right? So multiplied by h I omega p. That's what the gain is, and phase is minus 80 degree, right? So, and this is away from -1, we know that, and this is going to be, since it's not passing through this, then it's stable, right? As it approaches here, if it passes on through this one, this becomes unstable, and beyond that also it will be unstable. Why? Because it is going to encircle this point. Encircling this point means that there is something there. Yeah. So especially when you are encircling in clockwise manner. Yeah. The clockwise manners, you know that typically this point, when it is 0, for example in this case, if it is 0, when omega tends to infinity, it is 0. That means if this line goes here, and this will be clockwise, which will be going like this. When clockwise it is going like this, meaning that it is encircling -1 clockwise manner, and hence that really means that at least one time, right? So that really means that n equal to z minus p is 1 at least. That means there is at least 1 0 on the right side of the S-plane, and hence it is going to be unstable. So meaning that if this line is here, goes like this one, it's not a good idea. It has, so for stability it has to be within this circle of radius 1. Okay. Now with respect to that, we can see that this is phi, and hence from here to here, what we have gamma, and this gamma is nothing but phase. Gamma is phase margin, right? Phase margin. So you have two things. So you have -1, right, or 1 angle minus 80 degree angle you are measuring from there towards the like anti-clockwise you are measuring, and this is 1 angle phi. This angle measuring from here to here is the positive. This is the phase margin, which is positive. Yeah. Now what about the gain margin? The gain margin is nothing. We know that gain margin is kz is equal to 1 over this. Yeah. So g. So this is point. This is omega p. Let's call it p. This is point p. This we are talking about the p subscript refers to this point p. At this point, this is omega. Yeah. So we can say omega p is omega equal to omega p at that point. At this point, we have omega equal to omega p right there. Okay. Okay. So kz equal to 1 over g I p g I omega p h I omega p. Yeah. This is the magnitude of that 1 over like this one. Yeah. Hence the kz will be simply this value will be nothing but equal to or that tells you this gain G I omega P H I omega P is equal to 1 over kg, where kg is the gain, the gain margin, or we write it at kg. Yeah, so this kg. So what we get? How do you indicate kg here? Kg is from here to here. So from here to here is kg. Yeah. So kg equal to gain margin. Okay. So kg between from 0 to a point where the phase is minus 80 degrees. The phase is minus 80 degree here. Yeah. So this gives you 1 over, sorry, this is 1 over. This value is 1 over kg, where kg is the gain margin, right? Ratio. This is because the value is here, this actually, right? Yeah. Okay. Sorry guys, I made a mistake. Here we are writing G omega P. So point P is for us this point. Okay, this is the point, not this. Okay, so point P we write here. So here our omega P is at right that point. Okay. Okay. Now it's good. Okay, so looking at the stability, looking at this, you can find out stable or not, and how much is stable. So this gives you a measure of that. This phase margin, gain margin is that gives you. Looking at this one, you can say that if it is avoiding this -1, right? So if it is going like this one, this means this is stable, right? So this is right now, this is stable. When you have a positive phase margin, that means it's a stable. A stable, why? This is positive. This is positive. This is also positive. Hence, it's a stable. Yeah. This becomes if it's a negative, meaning that let us say if we had this going like this. In that case, what you see here, your phase, this point here, right here. Yeah. So what you see, your phase margin, right now it is gamma. Gamma is positive now. This becomes negative now. The phase margin is negative. Yeah. That's one thing. And the second thing is see here, and this meets this point. So what you see here, 1 over kg, right? 1 over kg. This is becomes a smaller value. So that becomes the 1 less than, from here to here, value will be from here to here, since kg becomes smaller now, so this becomes bigger. So this is bigger than 1, that really means, right? So the gain becomes more than 1, and that is negative. Gain being more than 1 at phase equal to 180 degree is not good, and hence it is here. Okay, and this tells you this one is not stable or unstable. Yeah. So this tells you unstable. This is a stable. This is stable. Yeah. Why? Because for the solid line we have positive, both of them, phase margin positive and gain margin positive. For this dashed line we have both negative. Yeah. So one point, instead of this point, you have this point now, which one comes before -1, the other, this comes after -1, and see here this comes below -180, below the real axis, on the dashed one it comes here, which is above the real axis. And okay, so that both of them are negative, and hence it's not stable. Okay. Okay, so regardless of, let us say, why it's not stable. Yeah, so maybe let us say if it is the clockwise, it is going like this one. Let us say you are going from here to here. Then also it has this included inside it. If this is included, that really means you have n equal to z minus p. So at least 1, 0 is there, right? Now if it is going anti-clockwise, then that really means n equal to minus 1, right? And in that case, z minus p equal to minus 1. That really means at least one pole is there on the right S-plane. Yeah, in both the cases, either you are going anti-clockwise or clockwise. As long as you are including minus 1 point, that really means it is not stable. As long as you are encircling this point minus 1 plus 0i, this system is not stable. Yeah. So, and if it is not encircling minus 1, and you know that there is no pole on the other side, then it will be stable. Yeah. So this is also like rephrasing the Nyquist stability criteria as well. But here, what we are looking at, how to look what is the meaning of gain margin and phase margin in both the cases, the Bode diagram and the Nyquist plot as well. Now question is, if you are given gi omega, hi omega, for that you have the Bode diagram which is plotted like this one. Then somebody tells you, what about the Bode diagram for k times gi omega, hi omega. What you are doing? You are multiplying with just k, and he tells you that tell me the Bode diagram now. So you can guess probably what you have to do is 20 log of that, right? And then 20 log of this, and what you see here will be equal to 20 log k and plus 20 log of this, the original one, gi omega times hi omega. That's it. You are just going to add this, meaning that right now this one is this part. This part is right now this one. On top of that, you add that, meaning that it will either go up and down depending on the value of k. Right? If k is more than 1, then it will be shifted upward. If k is less than 1, then it will be shifted down. And this is how you are going to design the system. If you want a desirable gain margin, phase margin, accordingly, if you move up and down, you can get that. Meaning that just a gain, like it is, for example, it will be a proportional, maybe the proportional control. Proportional control below, what will it do? So you have like k here, and then after that you have g, and then it goes here h like this, right? So like this one, this system. Okay, so if you know g, which you cannot change, or h also you cannot change, then you can introduce a proportional control, right? And we can change k such a way it is going to up and down. Accordingly, you can have the required phase margin or gain margin. Yeah. Similarly, the effect will be, you can see here, if it go up and down, similarly here also the curve will change. Okay, so here what we are doing, just introducing k here, it will, the effect will be, this will not change this one because phase remains the same, this will go up and down. But what will happen to this one? If you multiply k with gi omega, hi omega, and the original, let us say the Nyquist plot is this one. So how will the new Nyquist plot will look like? the effect will be just zooming in. That really means zooming in or out, meaning that phase remains the same as earlier. What you will see is like it is your radius. Basically, this one is -1. You can say this circle is either becoming a smaller or bigger, meaning that this is going to be like -1. It is right now here. Yeah. So let us say you are in the k is more than 1. Then what it will do? It is going to basically this is going to zoom this one, right? So instead of having like this one, it will go somewhere here. It will, if you have k more, so this something becomes like this one. So meaning that what you see here, this automatically, although we draw this for a different reason, but if you increase the k, for example, what you will get is this becomes something like this. It will be something like a zooming, right? You are it will this will become zoom basically, right? So it will go like this, or even more go like this one. Yeah. So even bigger k, it will go like this one. So like this, and so on. Yeah. Similarly, if you decrease k, then this becomes something like this. Yeah. So we looked at how we can change the gain diagram, yeah, without affecting the phase diagram. What you do, you multiply it by k, or you have the proportional control. Similarly, you can also change the phase diagram itself without much affecting the gain diagram, but it will be affected too. Yeah, but you can choose accordingly. The idea is the design, basically how to design a system so that you get the desired Bode diagram or desired Nyquist plot. Why desired? Desired meaning that it should be stable, right? So remember that all these we are doing because we want to design a system, and our system is basically could be this one, GS, yeah, and this may be this may have feedback loop, negative feedback loop is HS there, yeah, and then we have, sorry, this is minus, this is plus, and we have a controller here. Okay, so we have controller and goes like this one. Only thing is we don't know. So as we said, proportional control, we can have k here, and you change the k accordingly. You have control over the phase margin and gain margin both. So it is going to affect both of them, gain margin and phase margin, both of them. Yeah. So if you choose the right k, you will get the phase margin equal to 0. I mean, when phase margin is 0, gain margin is also 0. Yeah, both will be 0 at the same time. Yeah, so you can make both 0 also, both positive, both negative also. So if one is positive, one is negative, the other is negative. If one is positive, the other is also positive. If one is 0, the other is also 0. If one is negative, the other is also negative. Which one? Gain margin and phase margin, both I'm talking about. So what we have seen that if you have just proportional control, right? Proportional control, and for that we saw that the gain diagram is going to shift up and down depending on what the value of k. If k is more than 1, it will shift up. If it is k, if this is less than 1, it is going to shift down accordingly. It is going to affect both the gain margin and phase margin, both of them. Similarly, you can have different k. You can have a differential, so you will have k times s or PID, all kinds of control you can have, and accordingly it is going to affect that also. Similarly, you can also have what is known as the compensator. right? So you can have lead lag compensator here, and what is going to do? So compensator, right? So compensator. When you say compensator, you know that if this will have something like T1 S plus 1 divided by T2 S plus 1 and multiplied by some, there may be some K as well, right? So say K times like this. So K times like this one. Okay, so when you have that and you know that you have this divided by this, that really means that this is going to, accordingly you can have flexibility to make to add a phase to it. Yeah, so you can either increase the phase or decrease the phase. Yeah, so that way also you can control the phase margin or gain margin accordingly. So this compensator also is a good tool to accordingly do it, and hence compensator is also a controller. Right? So this is for controlling, to making the system more stable. It's possible that GS you cannot, this is a plant, so you don't have much say there, much control on that, and this depends on also the sensor and all. So HS may also be given basically for you. So only thing here, this is a controller or compensator, you can put it here. Accordingly you can tune it such a way that even if this plant is very close to instability, you can make it stable just by increasing the phase margin or gain margin, right? And then it will work. So this is basically design. Yeah, so this is you may be more working during your lab basically, but finally this course is about finally designing. It is not just understanding but designing also. So here, although we did not go into details of that, but remember that the compensator can change the phase margin and gain margin, yeah, as it does in case of the just a gain, introducing the gain there. Okay.